is actually just I and P12, P23, P34, Pm minus 1, n. And now this is really beautiful because what it does is that you're starting from one side of spin, say at the n side, do a permutation. It's like you begin with the lattice side n, and you kind of swap it with the neighboring side all the way to where you started from. So in some sense, you are propagating whatever spin state. You begin from one end to the other side, or you go around the loop if you want. Okay. And what do we call this? Well, of course, we call these things like a momentum operators. So I denote something like this just to take care of the factor of In. And this is nothing but P. This is the momentum operators of this lattice system. And also you can also show this as P is actually real, and so therefore this guy is a unitary operator and so on. So that's why that in the literature sometimes you will see that, well, you know, those lax operator which you use to build these transfer matrices will interpret it as something like take you from one lattice side to the next one and so on. But I think it's more obvious, at least to me, that after you did this manipulation, that you can say, well, the transfer matrix indeed, at least at a special value of a spectral parameter, is precisely what bring you from one lattice side to another. And in fact, by periodicity, you can starting from any given point here, and you just come back to itself. Okay. So that was the momentum operator. So let me just write down. Okay, I just we can write about this. So now we want to get back to the Hamiltonian. So of course, a lot of steps. I mean, if you find it hard to follow, it's simply because you do not have time to actually go through all the calculation on step. But hopefully, you could try. For those of you interested, really try to, get yourself familiarized with this, the operation on this tensor space of tensor of the vector space. So we have now we have the momentum operators. So now similarly, we can consider the differentiation of the transfer matrix with respect to lambda. And we set lambda equal to I over 2 again. Because another thing you should remind yourself is that the way we write down a Hamiltonian. But in any cases, this is what it is. So this one indicating that the particular permutation operator P and A is actually missing in this term, then you basically sum over all the possible, any each of those one will be n minus 1 permutation operator multiplied together. So again, we do the same trick that we trace over A's. So we would get the lambda FA lambda equal to I over 2 is equal to I at minus 1. P12. The key here is that because this term is missing, you can show that the permutation term now is actually permuting the n minus 1 side and n plus 1 side. And then continue. Yeah. But now if you compare with, compare this guy with what we have here, then if you multiply them together, then go through the manipulation. So that's actually just a simple, I'll actually give a clue how to prove this in the notes. But if you now consider this one, this is precisely after you've done all the permutation. This is this guy. Then you saw, aha, I have seen this one before, because this is what, if you recall what a Hamiltonian, but it's almost like Hamiltonian, that this is this one, right? Then I minus pi is some factor of 2 or something. Okay, so that's basically saying that, probably 1, whatever. So that's basically tells you that the Hamiltonian is basically this guy. So this is basically log FA, right? So the lambda log FA lambda minus n over 2. Then we have it because, well, sorry. So lambda equal to I over 2. So well, we basically have this one. Right? Is it obvious to people? Because coefficient of f lambda are the q's, and now we show the h is a function of f given by the log derivative. And this guy n is just a constant. Of course, it commutes with everything else. So basically, the function h can be expressed as a function of q's, and therefore, because we know qk equal to 0, this implies the Hamiltonian also commutes with all the conserved charges. So what do we have? So now we actually have n. So if you throw in the spin, the total spin, and the q here, there are n minus 1 of them, and we show the Hamiltonian conserved with q's. And therefore, we also show h commute with spins. So the end product we have now is that we have n conserved commuting charges for our spin chain, and that precisely established the quantum integrability. So this is, if you want, this is the quantum mechanical statement of a Liouville theorem, an analog of Liouville theorem. So we have n commuting conserved charges or operators or physical quantities, whichever way you want to do it. Satisfy Q 0. So this, if you want, it's a QM analog of what we had before. So the actual variable, or basically the conserved quantity, what we established the Liouville integrability. Okay. So now we have shown the spin chain is really a quantum mechanical integrable, well, quantum integrable system. This formalism actually does even more. Because a lot of time, we are not just only interested, okay, fine, solvable. But what we really want is actually a wave function that for the spin chain. And we can actually construct it, actually. And this is actually something like a generalization of a simple harmonic oscillators. And in the process of finding the, I guess, the eigenfunction for the spin chain Hamiltonian, we will derive the Besser-Ensat equation for spin chain. So basically, if you want, it boils down to the process of finding the eigenfunction for the spin chain Hamiltonian is actually trying to solve the so-called Besser-Ensat equation. And there are various techniques one can do this. I mean, which I don't have time to. I mean, unfortunately, I won't have time to talk about. But that's where your research starts. So, okay, so we want to find, actually more precisely, we know now H is one of the, it's basically a function of those conserved charges, which are coefficients of this function f lambda. So what we really want is finding the eigenstate for f lambda. And the way to do it is we now actually think about, so I'm even dropping n here now. So you should really recall this is actually operator acting on the spin chain side. But on the auxiliary space, that's the representation. So we want to generalize. So to find to do so, we generalize the simple harmonic oscillator. How do we do it? Well, so if you recall that they are raising and lowering or creation and annihilation, depends on which text you read. Operators allow you to solve for a simple harmonic oscillator. And basically the punchline is that you want to work out, there's a ground state which get annihilated. So this is a way of writing it. So the Hamiltonian for the SHO is basically numbering operator telling you how many modes you're actually setting. Okay. So, and the way to do it is really that, okay, so let's find ground state, which is going to get annihilated by the annihilation operators, or null ring operator, which actually equal to 0. And then this usually boils down to some differential equation, then you solve it, and you discover this is something like Gaussian wave function. And then all the excited state, or the other eigenmodes, you simply act on the ground state with all the creation operator to whatever number of modes you want to be excited. Higher energy space. So basically, we want to do exactly the same thing with the spin chain, and we want to derive an analog of this kind of creation and annihilation operators. Then the first thing we want to do is to find a ground state, and then get killed by all the so-called creation operators, sorry, annihilation operators, and then you act on ground state to get your all the excited states. Okay. So where's a good place to start? To do so to actually work out what's the analog of this guy for the spin chain, well, so we can express, we can introduce some bases. And express the spin chain, express the permutation operator and R matrices and so on. So, okay, so the basis I'm going to introduce is something like E plus equal to 1, 0, and E minus equal to 0, 1, and sometimes this goes spin up and spin down state. So, so in this basis, we have a permutation operator, which would be a 4x4 matrix, which is looking something like so, and the R matrix would be something like A lambda, B lambda. All we do is fine, not bad. Okay, good. So, I'm going to jump a step ahead, so get to the point. That so all these functions are specified in this. You should be able to get it now. So the punchline is that you can, in this basis, you can write out the fundamental commutation relation 2, which is basically a transfer matrix. And the R matrix, you can write them out in terms of components like A, B, C, D. And they gives you, at least for the pieces we want, I guess they're right here, they gives you the following. So the step can be found in the notes, but if it's too hard, just a second now. So, but it's really just a kind of algebraic manipulation, or you can put it on a computer if you really want to. So those three are the ones we need. There are other terms. There are other relations. But those three are the components. So it's really easy to work out. Just use those bases and do the matrix multiplication and stuff. Okay, so why do we need those three? Well, so basically, so 2 and 3 are the spin chain analog of the SHO relation, simple harmonic oscillator relation, when you add a creation or annihilation operator on the number operator. Okay? So it's kind of raising and lowering relation you want. Okay. So now we can actually have a ground state. So we want a ground state such that so some of you can already guess the ground state. Can any of you guess what the ground state is? In this case, what will be looking like? The spin half. Has anyone heard ferromagnetic ground states? Yes, I hope. And it is. So basically the ground state omega is such that the C lambda omega is equal to 0. So and omega is actually constructed by n e plus n. And this is equal to 1, 0, tensor, 1, 0, tensor, 1, 0, for n of them. So actually, so this is actually the one that cannot be raised any further. Okay, so what does it look like? This is actually this one. All the spin along the same directions. And we know that for this state, for example, if we have a lax matrix, so a lax operator acting on, say, nth state here, so what does it do? Well, okay, we know this guy is looking like, just remind you. Plus, so those plus and minus are really a raising and lowering operator when you're looking at the SL2 algebra. So this guy, when you act on this, actually give you 0. So acting on 1, 0 is actually lambda plus I over 2, lambda minus I over 2, 0, and there's some junct. Okay, so it's a triangular, it's an upper triangle matrices. So when you look at the other transfer matrix, going to act on this, or the tensor product of all these 1, 0 guys together, it basically looks like this. Some junct. Because individual side, let's just give you those contribution, and it's an upper triangular matrix, and you are multiply n of them together, and of course they remain of a triangular matrix, and the diagonal entries being just, this guy raised to the power n, and we have it, because now take the trace, so this would be A here. Well, basically, if we trace A and we get an F operator, so F lambda acting on omega, this, so that's basically so omega is the eigenstate of F lambda. Sorry, yeah, F lambda with an eigenvalue given by the following. And this is the ground state. So this is actually, and this is precisely the famous ferromagnetic ground state. Okay. So now, given the ground state, then what do we do next? All we can do is changing the spin, right? Flipping down the spin from up to down, and so on. And to do that, we can consider, so just like in the simple harmonic oscillator from ground state, then we will want to act on it, kind of creation operators. And this is something like this, so we're acting a certain number of them, each of them associated with a spectral parameter. And in fact, all these spectral parameters are going to be related to the momentum carried by the individual excitations. So cut to the chase, for those of you who have studied some level of condensed matter physics, that each of those guys is a creation operator really for a whole, because this is actually spin off. Then what it does is actually flip the spin to spin downstairs. And the lambda here are actually the momentum carried by those holes. So of course you can flip the entire Hamiltonian by minus signs. Then all these guys become like this. Then you flip it off, then you have all the excitation can be interpreted as some kind of magnet. They are really equivalent for that part. Okay, so basically make some guess for what the eigenstates. So we were basically proposing this guy is going to be an eigenstate of the Hamiltonian. So we demand, by demanding it to be the